So we're in chapter 5, section 3, and we're going to be talking about gas laws. We're going to go over quite a few. I think there's probably at least 5 different laws that have to do with gas and how they came to be. And actually, they're comparing certain variables in gas. Well, how did this all get started? Well, we have one of the laws. The first law is Boyles' law. And Boyles' law has to do about volume and pressure. Well, who was Boyle and what is Boyles' law? Well, Robert Boyle, he was a scientist during the 1600s, 16 to 1700s. The scientists discovered that gases behave in orderly ways. And so he was seeing basically how the gas in the volume of the gas compared to the pressure of the gas. So he was doing an experiment here, and this experiment was that Boyle used mercury to trap small amounts of air in a glass tube that was shaped like letter J. When Boyle poured the mercury into the open end of the tube, the bend in the tube there trapped a small amount of air there and formed columns of mercury on each side. The pressure on the trapped air could be calculated by measuring the difference in heights of the mercury. And so that's just what he did. And this way he could compare pressure and volume. And that's what he was doing. So in the midst of all this, Robert Boyle was beginning to, through his hypothesis, he ended up bringing forth a law that we have even today that have to do with gases, that pressure and volume can compare, and they're in an inverse relationship to each other. Let's find out what an inverse relationship means. Here's, as pressure goes up, the volume goes down. And as pressure goes down, the volume goes up. And so here, but you have to have it at a constant temperature. If you change the temperature in any way, then it's going to affect the pressure and volume, which all three of those things go together. But as we go, as the temperature is constant, you'll see that pressure and volume are inverse to each other. That's what we called as the inverse relationship between each other in proportions. Here's a picture of it. You see here, as the pressure here is a 250 torr here. See how these molecules and the pressure in the midst of it kind of represented. And as the volume is 1,000 milliliters. Well, as we decrease the volume here, the pressure is going to increase. See, the pressure goes down and it's actually being compacted. The pressure in the water here, or in the air, I should say, it's not water, and the air is going to be tighter. So here we go on to the pressure of 750 torr and 330 milliliters. So you can see the inverse relation up to 1,000 torr to 250. So what it's doing here, as you can see, as the volume decreases, the pressure increases in gas. We're not talking about, I said something about water. It looks like water here, but it's not, it's gas. This does not behave the same way in water. So here we have this relationship. Here's another picture of the relationship here. So the picture here says, Boyle's law explained. And you see here, you see the pressure of the gas there and the flask with the volume. And now you have a smaller flask with the volume 2, and the pressure is higher in the midst of this. So this is Boyle's law. See how the pressure and the volume are inverse relationships. So let's go to my notes here a little bit here, and we'll go over it a little bit more here. Okay, sorry. Gas laws here. So we have the gas laws. Pressure and volume are compared here, and as I said, the inverse relationship. And now we have V means volume, and then volume is inverse over 1 over P. So this little sign right here is the sign of proportion. So it means volume is proportional to 1 over pressure. So volume is proportional, and here we have 1 over pressure, or the reciprocal. So Boyle's law says at a constant temperature, that means the temperature has to be constant. You can't change the temperature. It has to be the same. Volume varies inversely with pressure. So here's volume that we have. Volume equals K over 1 over P. You take that and you move this P up here, because basically it's on this side, so algebraically move it up here. So we have P times V equals K, constant. But if you are going to find a variable to solve any problems, the best way you're going to do in solving problems is to use the equation with pressure and volume. The first pressure, the first volume equals the second pressure and the second volume, and then you make it into equation. We'll find out how to do that in this example. So the example in your book says, let me go ahead and read it here. A flexible helium-filled weather balloon has a volume of 500 liters at a pressure of 1 atmosphere. What will be the volume of the balloon when it reaches an altitude at which the pressure is only 0.5 or half atmosphere? Assume the temperature has to be constant for this to work. So basically we have this helium balloon. We have 500 liters at 1 atmosphere. This is the pressure, and this is the volume. So we put down, what is the first pressure? The first pressure is going to be 1 atmosphere. Okay, the volume is going to be 500 liters. Always remember, liters are volume. You know, if you're going to drink a liter of Coke or whatever, it's going to be a volume of Coke. So 500 liters. So now we want to know what it's going to be at 0.5 atm. That's the measure of pressure. So remember, it's 600. One atm is 760 torrs. So here we have. So I put down P2. So now what is V2? Well, V2, basically V2 is what we're looking for. We want to know what the volume will be. So now we can fill in the blanks. This is how you do. Basically, just like you're doing an algebra problem here. You're going to fill in the blanks. So see how, make sure this, there we go. So see how we do here? We're going to say, fill in the blanks of P1, V1 to P2, V2. So that's what I did. P1 is 1 atm and V1 is 500 liters, right? That's what we found out up here. And now we're going to put down 0.5 atms and V2. So now we want to find this. Well, algebraically, we could put this, this has to go in the reciprocal. So then we have 1 atm and 500 liters divided by 0.5 atm. So that's what we did. So we got rid of the ATM there. So now all we have is 500 liters divided by 0.5. If you do that, you're going to get 1,000 liters. So it's going to be 1,000 liters. So helium boom, what will be the volume pressure? As the volume, as the pressure goes down from 1 atm to half an atm, the volume is going to go up, and it does. It goes up from 500 liters to 1,000 liters. So the volume should be greater than the lower pressure. So that's how you do. You're going to have some problems like that. They're actually pretty easy, but you have to make sure you just use this formula here and then put each pressure and volume, and then make it into, you're going to have this equals each other, and then just make it into a problem and fill in the blanks. So we can do that. It's not going to be too hard. So just remember and review Boyle's law. And review of Boyle's law, right here, Boyle's law has to do with pressure and volume. Temperature has to remain constant. So, and it's always in an inverse relationship. As one goes up, the other goes down. Okay, that's Boyle's law. So now let's go on to the next part, which talks about another law, and this is Charles' law. Well, what is Charles' law, and what did Charles do? Who is Charles? So let's look at this in your book. So Charles' law here. So here it talks about Charles' law. Charles' law talks about, as you see, volume and temperature. Now we don't have pressure anymore at all in this case. He's just looking at volume and temperature. So back around the 1800s, Jacques Charles. His last name was Charles, Jacques Charles, and he lived in the 1700s, 1746 to 1823. And his a scientist that was working with him too, was named Joseph Guy Lussick. And Joseph Guy Lussick lived the same time, 1778 to 1850, so he was younger. And working together, they studied the effect of temperature on volume of the gas. So you may be familiar with the effect of temperature as the balloon goes up, or as a balloon, actually that goes up, as the balloon is placed in a warm place, the volume may increase so much that the balloon bursts. So what happens? Temperature causes the volume to go up. We're talking about temperature and volume. And so he went over here, temperature, supposing there's 273 milliliters of helium gas at 0 degrees. And then they found as they increased the temperature, 1 milliliter for every centigram or centimeter, or I should not say centimeter, for every Celsius, 1 degree Celsius, its volume increased, right? So here it kind of tells about that whole situation. So going on, let's look at the photo and you can kind of describe it here. So here we have the temperature and it's heated up. So here we have, as the temperature is heated up, and these volumes of gases, remember they're gases, it looks like liquid, but they're gases. And as these are heated up, the gas expands and takes up a larger volume. So when it's heated up here, this is 400 K, that's Kelvin scale. This was 200 K, so 400 K, it's getting hotter. It goes from 250 to 500 milliliters. Then when it gets to 600 K, which is 100 degrees Kelvin higher, it goes up even further to 750 milliliters. So as you heat up this gas, the gas expands and takes up more volume. So that's what they're talking about. This is a direct relationship. That means as temperature goes up, volume goes up. It's different from Boyles. Boyles is just the opposite. So, and here is a picture of a direct relationship on a chart here. You have the volume of the temperature going up this way, and as the volume goes up, the volume's going up, the temperature goes up. So here's the temperature going up in this side, and you chart it, and it looks like this. So whenever you have a graph like that, you're going to have a direct relationship. If you have a graph going the opposite direction as my pencil is, it will be indirect. So, but there's one thing that Charles and Guy Lussick found, and they found that it doesn't work with scales like the Fahrenheit scale. When you take temperature with Fahrenheit, it doesn't work with Fahrenheit, and it doesn't work with centigrade. In fact, you have to have an absolute scale, and the only absolute scale we have is absolute zero scale with Kelvin. Thus it says, when working with relationships between temperature and volume, you must convert Celsius temperatures to an absolute scale. And that is the scale that we have heard before, absolute zero. And we'll see, remember how to change this to absolute zero. So in fact, all you have to do to change it to absolute zero is add, basically add 273, where is it? 273 and 15 tenths. So, so going on, let's go on here. Let's go on. Let me show you my notes, and that way you can see how these things work here. This is Charles' law. Okay, in Charles' law, the volume and temperature are directly related. As one goes up, the other one goes up. So, and they're only proportional if they're in the Kelvin scale, which is absolute scale. So you have to change Celsius to Kelvin, which really all you have to do is add any Celsius degree 273.15. So most of the time, with ease, they'll just round that to 273. So you're going to add 273 to the Celsius. Charles' law states the volume of a given amount of gas at constant pressure, that means pressure has to remain the same, you can't move the pressure at all, is directly proportional to the absolute temperature. Absolute temperature means you have to use the Kelvin scale. So here we have volume is proportional to temperature. The volume equals, this is the constant, times temperature there. So, or the volume is going to be, you put the temperature on this side, the volume over T equals K. So when you're doing a problem that's directly proportional, you're going to use it like you're going to use this. Basically use this to find, if you have one volume, to find another volume, or one temperature to find the other temperature. So you have the volume, let's move these up so you can see it better. So you have the volume over the temperature, so the volume 2 over the temperature. And before you can scale them, you can, before 0 Kelvin, molecules liquefy and solidify. What they're saying there is basically that there's no, when you get down to absolute 0, the lowest temperature you can get, no substance exists as a gas at that temperature. So it solidifies. So when you get down to the absolute 0, this doesn't work anymore because no substance will stay as a gas. Okay, just a note in case you get down to that low of a temperature. So now here is the problem that we have. Let me find it and read it to you. A balloon has a volume of 1,000. Let's move it up so you can see it better. The balloon has a volume of 1,000 milliliters at 300 Kelvin, which is 80 degrees Fahrenheit. If it is placed in a laboratory freezer with a temperature of 200, that means the temperature is going down Kelvin, which is a negative 100 degrees Fahrenheit, what will be the new volume? Okay, let's find that out. So we looked here, we placed it in the freezer, so it's going to get cooler. So here we have the first temperature is going to be what? 300 Kelvin, right? The first volume, what's the volume? Is going to be 1,000 milliliters. The second temperature is going to be 200 Kelvin. So all you got to do is put it in that formula. So we put down V1, V2. So what is it, V1? V1 is 1,000. So we put down 1,000. T1 is 300. So we put down 300 here. And then T2 is 200. So we put that as T2 right here, T2. So you should put down the milliliters and cross out the milliliters because we're going to look to see, or cross out the kelvins. I should put the kelvins. But anyway, this is the problem here. So then you just fill in the blanks. So 1,000 and 1,000 milliliters, 200 kelvins, 300 kelvins. So you can cross out the kelvins there because you've got one on the top and one at the bottom. And then you'll have 1,000 milliliters. I crossed out 2 of these zeros and 2 of these zeros. So you have 1,000 times 2 is 2,000 divided by 3, which is 667 milliliters. So we look at this. As temperature decreases, volume decreases. Yes, the volume decreased from 1,000 to 667. So that's the equation. So you need to know, basically, you know this because we're going to combine these two laws and put them all together. But right now, this was Charles' law. So let's stop there, and we'll go on in the next video. We'll go on with the other laws.